So we talked about on Tuesday the antiderivative, and we were basically looking at just doing the inverse of the derivative. So we were looking at the derivative rules and basically just doing the opposites of them. So that leads us into what is an antiderivative, and we've talked briefly about it, so it's an integral. But what is an integral really doing? So if we talk about a derivative, we know what it's doing. It's finding the slope. It's finding that change. Okay? So if we're going the other direction, what's an integral actually help us find in terms of the information? So, and what an integral does is it basically helps us find the area under a curve. So here's a few really simple ones. We're like looking for the area of a rectangle. It's easy. It's just length times width. It's fine. Triangle, it's half of rectangles. We just basically cut that in half. We start to get more complicated shapes. You have to start adding up those pieces. But what happens if I wanted to find a curve that looks like this? If I wanted to find a shape that looks like this, how would I find the area of that? Well, yes, because that's kind of what we're talking about. But how would you do it? Like, if you didn't know integrals, how would you do it? They do it in circles?
First, I will find like what the curve, what the function of the curve is.
Where
Like
it's somewhere it's min and max of the
circles?
no, not like that.
like,
Yeah,
like circle?
Because it looks like there's a circle there. So yeah, figure out how
Oh yeah, don't yeah.
So separate that's how min and max.
So if we like separate it here,
yeah, and then one chunk is that's one chunk.
right? So then the question is how do you find this chunk, or are you just going to make it a rectangle like that?
So
Yeah.
Like something like that.
Huh?
Something like that.
Yeah.
I remember.
So then if we made one over here, but then we're missing we have this chunk up here that's not really needed, but then we have a chunk down here. So it's a matter of how do you break it? So like this piece up here was pretty simple, right? We just broke them down into some triangles. So you actually really do want to break it down into rectangles. The question is how do you break it down into rectangles so you can find the right amount of pieces? All right, so if we look at, so here's a simple curve. Where did my erase? There's. So here's that's the curve I'm looking at. So it's just y equals x squared. So if I wanted to find that area right there, we can do some simple ways. This is one method we can do. We're just breaking it down into some rectangles. We're splitting it up into quarters. So we cut this shape down into 4 pieces and found my rectangle. So this rectangle is always using the end point. So we're looking at it. We're taking the end piece there, going across where it put there. So we have pieces on the outside that are extra. And if we did the other direction, we have pieces on the inside that we're missing. Okay. So that would work, but that might not give me a very good estimation on what the area is.
I think it's considered both the left and right side.
Yeah, so let's see if we look at this one. Now this one's breaking it down into smaller chunks, right? This is breaking down into 8, so there's 8 rectangles there now. And you notice that the pieces inside are a lot smaller, so I have less there, and there's less on the outside. All right, so now think back to when we first started derivatives. When we were looking for slope. We didn't find the derivative off the start. What were we using? We were using limits, yes. We were using limits. And limits allows us to take, basically at that point, we're looking at the 2 points, right? And we're getting closer and closer together. So basically, the distance between those 2 points was what my limit was. I wanted that to go down to 0. So if we're looking at this, I went from 4 to 8. So we're going to do something similar. Like if I took at that and look at the limits, and I'm looking at the width of those rectangles, getting smaller and smaller. Eventually, if they get down to basically nothing, it would be the original curve that I had. So it would be that original curve right there. So what they did was, they did this. So if I did 10 rectangles, the sum of the left, which is the one underneath, was 0.285, and the sum of the right was 0.385. Hold on a second. Yes? Okay, and I'm in class. Okay, I love you too. Bye. Like I hung up and then she called back. So normally when they call directly back, something's wrong. Alright, so we did 10. And we have that range on either side, we know that. So if we go down to 20, they're starting to get closer. 30, they're getting even closer. 50, 100, and 1,000. Okay, so as the amount of them get bigger, that means the widths get smaller. That means the extra piece on the outside or inside gets less and less. And we start getting closer and closer to what the actual curve was. So if we look here, this is getting pretty close to 0.333. That's 0.333. So if you were to guess what the area under this curve would be, what would you guess the area would be? 0.333, which would be what?
1/3.
Right. That would be 1/3. So, before I go on to the next piece, the function that I was just looking at was what? Y equals x squared, right? What's the antiderivative of that? So if I said that's y prime,
y would be
1/3 x to the third, right? Now we were going from 0 to 1, correct? So if I plug in 0 to this, I would get 0, right? If I plugged in 1 to that, I would get 1/3. Okay, so the antiderivative, or the integral, basically is a way for us to find area underneath any curve, as long as we have a curve, an equation for that curve. So that was all of section 5.1, by the way. That was literally what 5.1 talked about. Yeah, except they made you do a ton of limit problems. And I'm not going to make you do a ton of limit problems. They made you do that. Find the area of these with the breakdown there, and then find the area of this one with the breakdown there, and then do the limit to go. Yeah, a lot of work. But you just, the key with that is understanding what it means so you can use it. Because the next step, once we look for area, we can find the area under the curve. That's easy to do with an integral. The more methods we find, the more complex of an equation we can do. But that also allows us to be able to find volume if we rotated it. It allows us to find surface areas. Again, same thing if we rotate it around. You can rotate it around the x, rotate it around the y. You can have holes in the middle of it. And then we can actually use integrals to find volumes of very complex pieces. So you can start to look at how that can expand out. When we're looking at a more application process, you can look at integration to use to find hydrostatic pressures on dams because the way the dam shapes are, it's like how much pressure can it take. Same thing with like blood vessels and pipes. You can use it to figure out probability, because like for statistics, it's the area underneath the curve. You can find different parts of it. Same kind of concept there too. So this is the integral symbol. So this is a definite integral because the definite integral has the numbers on the top and the bottom. So we're looking at this one from A to B of that function. Basically, all this is saying is that it is the limit of the sum of all those rectangles. Okay? So only piece that you have to know is that the integral has to be, the function has to be constant, or not constant, continuous under that curve, under that range, whatever area or the domain you're looking at, or interval you're looking at.
So when it's discontinuous, when there's a hole, do you then divide it by before and then after the hole?
Yeah, so if you have, holes don't come up as often as asymptotes do. So if you have an asymptote, like this one actually has a horizontal, the one we just looked at, actually no, x squared didn't, but if it was like 3 to the x, it would have a horizontal asymptote. But if you have an asymptote in it, yes, you would look at prior to the asymptote point and then after it if you wanted to. But definite integrals you don't want to go to infinity, because if you go to infinity, your area is infinite underneath it. So you have to look at where is it going to that point. If you're looking at it in terms of a definite value where you kind of come up with a specific number out of it at the end. So if we're just looking at coming up with the equation, you just come up with the equation. All right, so let's look at one. So here is the first integral we're going to do. And that's what it looks like. So that's actually what the area looks like. So one of the things I say, we can use it to find the area under the curve. However, it's not considered exactly the area under the curve, because one major piece is area can never be negative. So, and if we look at this, we have area down here, and we have area up there. So it's actually, it's this, let me try the right words to explain this. It is the amount of space between the x-axis and the curve. Okay? Now, that can be positive or negative. In this case, the A2 section is going to be negative. That A1 section is going to be positive. So when we're doing the integral for this one, we're just going to find the integral. It's going to take that into account and actually do that subtraction part. Okay? And I need to figure out exactly where this crosses the x-axis, because I want to do one more thing with this. So first step, I want you to do the antiderivative of x to the third minus 6x. So find me that integral.
One before one to the power of 4 minus 3x to the power of 3. plus C.
Now, when you're doing a definite integral, just like when we're looking at plugging those things in, you don't need to find the C because we're going to plug numbers into the problem anyway. So we don't need the C for these. Yeah. So anytime we do a definite integral, you do not need the C. That's minus 3x squared. So everybody got that, correct? Okay. All right, so we're looking at this from 0 to 3. So when we're doing this, what you end up writing is you end up writing it like this. And we're evaluating it from 0 to 3. You plug each one in, you're subtracting the small one from the big one. So we're going to plug in 1/4 x to the third, not x to the third. And we're going to plug in 3. And then we have 3 times 3 squared. And then we subtract the 0 one. So same thing. So this part is just 0, so we don't have to worry about that. So it's 3 to the 4th. Is 81. So I have 81 over 4 minus 27 minus 0. So base 0. So 27 times 4. So I got 81 minus 108. So I got 27 over 4, which this one equals exactly 6.75. And it's negative. Does that make sense? All right. We're now going to do the exact same problem, except I'm going to change the ranges. Here's the nice thing about doing this. We already did the integral. So we already have this. So if I change these numbers, this doesn't change because you did this without those two numbers, right? We did this part here, irrespective of the 0 and the 3. Like I could have made those numbers anything I wanted, and you still would have given me the exact same answer here. Correct? Okay. So now, if I change those numbers, we can just plug them back in there to find that thing, or find the actual piece that we're looking for. So this number right here, that right there, is 2.45. So what I want to do is I want to show you that when they do the areas, it's the two areas, and they actually do end up just putting them together or subtracting them.
Wait, how did you find 2.45?
I graphed it and found the intersection point. It does.
Oh, that's only one.
It does.
Like that.
Oh yeah, this is gonna give me the exact same answer. You do not have to do this. I'm just showing you that it does do that subtraction thing that I just said it did.
So when we're looking for that area, you expect a negative value as an answer.
In this case, we're gonna have a negative answer because this area is bigger than that area.
Okay.
There's more underneath the x-axis than above the x-axis.
My teachers always forced us to do each individual area separately and then add them together.
So it depends on what you're looking for. Okay? So, and this is where that's why I said it's not necessarily the area under the curve that you're looking for. It's the space between the curve and the x-axis. So if it's above the curve, it's going to be a positive space. If it's below it, it's going to be negative. So if you're looking for, if we're going to rotate this around, yes, you'd want them both to be positive, because if you're going to rotate it around, we want actually that positive area. So you would end up having to break it down into pieces to find the two areas. Okay? For this problem, though, when we're looking at evaluating from 0 to 3, the answer is negative 6.75. It's not the sum of those two areas. Okay, does that make sense?
Okay, so when it's like evaluate, that means just do distance from x.
Yeah, so it's just doing those two pieces. So it's really, like I said, a lot of, even like with the derivatives and stuff, it's a matter of how you're using it to figure out what you want. In this type of problem, normally, they wouldn't have set the range to split it. They did it on purpose because they wanted you to see that it's not actually a full area. That was kind of why we were doing this problem. Yes? Oh, I did 81 over 4 because it happened to come out to be the same number. 27 is really 108 over 4. I just common denominator, and it ends up being negative 27. So the 27 didn't move over. It just happened to come out to the same number. And it was, what was it, 6x. All right, so we're going to do this from 0 to 2.45. So we're going to take the exact same thing you just did, the 1/4 x to the 4th minus 3x squared. And this time you're evaluating it on 2 and 2.45. And then we're going to do the same thing, but this time we're going to do it from 2.45 to 3.
Now, what is the purpose of doing 2.45?
I'm showing you that when you're looking at these two pieces here. So notice how this one crosses the x-axis. So originally when I said that the integral is taking the area under the curve, okay, which it is, but that concept of area has a very specific meaning in our minds. And if I'm looking for the area of the floor, or the area of the wall, or the area of things like that, it's like there's a very specific meaning on what area means to us. And in that terms, area cannot be negative because it's space. Okay? So if I did this problem out and we got negative 6.75, and I didn't say anything about that, somebody, like he actually just did a second ago, would have said, well, why is it negative? He didn't say why it was negative, but he asked, like his other teachers had them split it up and add them together. So it's because you're looking at the distance between the x-axis in this case and the curve. And sometimes that can be negative because you're going below the x-axis. And sometimes it can be positive if you're above the x-axis. That's acceptable. Okay? Now, depending on what you're doing with this problem, if I was taking this and rotating it around to get a base, which we could do, my area wouldn't end up being negative in that case. I would have to actually split it at that point, which is what I'm going to do right now at the 2.45, and say, okay, we've got the piece before this point and the piece after this point as my area that I'm rotating around. Right? So you have to have the understanding of what that means in terms of your visualization and understanding it. Does that make sense?
Yes.
Okay.
How do you read that? That's 6.75 units is actually below from 0.03, or is that like average? Or?
No, that's actually the entire space. So it's like, so I guess you could say it's the, if you were going to make this as a rectangle, because in essence, that's what this would be. If you were to make a rectangle to mirror the area of this curve, it would be underneath the x-axis and have an area of 6.75. Does that make sense? Okay. We're going to do, like I said, splitting it up is going to help you a little bit understanding the pieces behind it. That's what we're going to do in a second, just so you can see why it's subtraction, why it's a negative, and those type of things. Yeah. If you're looking at the integral of it, yeah, it ends up coming out to be 0 at that point. If you're doing it as a definite integral over from 0 to 2 pi, because it's an equal above and below. That's why a lot of times you don't do that. So when you're looking at because we found the integral of sine is negative cosine of x. So, and that's the thing, it's like, that would be the entire curve. Now you could take that and figure out each piece and find the answer to it. And again, same thing, if you went from 0 to 2 pi, you're going to get a 0 answer. Because one's going to be -1, one's going to be +1 at that point. And it's going to come out to be 0 at that point. So it'll cancel itself out. All right, so the 0 we don't have to worry about because we know it comes out to be 0. If I plug in 2.45 to this, what do I get? I think that was A2. That was A1. Because I think, yeah, they actually did it that way, which is fine. I don't know.
Trying to make it square split down.
I don't know why they wrote it that way.
That's like subtracting.
No, yeah, because I think that's because they're trying
Maybe.
to make a square circle from the top, I think, goes down.
Maybe. In the great, it's overall, that's not that big of a deal.
Well, I mean, that's what I think it is.
It might be. All right, so what do we get when we plugged in 2.45? There's no way you're doing this in your head. You're going to have to use a calculator. That's why I asked, because I feel like grabbing my calculator really quickly. Actually, I'll show you one other thing, because actually this is kind of nice. Remember we used Desmos?
Oh, you can graph?
You could graph, but that's not going to help you much in this case.
No.
But you could do...
Wait, they have a decimal calculator?
Yeah.
I did not know that.
And you could plug in whatever number you want for x. So notice how I just plugged in that and I got basically -9. So you could take and plug the equation in there and then just change x. And it'll just change the problem. So if you're going to do multiple values of it, you can do this and it'll give you multiple values. So this comes out to be -9. So in this case, I've got whatever 3 is minus a -9, because we're going to subtract off the end. So now I'm just going to plug in 3. And I get -6.75. So this is going to come to be 3.25. So that's positive 3.25, and that's -9. So area 1, which is the piece above, has an area of 3.25. Area 2, the spot underneath the curve, has an area of -9. We put them together, that's how we get the area of the -6.75. That would be below the curve. If you were looking at, if we put them all above the curve, so we were looking at that area, so if we're going to rotate it, the area actually would be, you'd add those two, you get 27 or 12.25 would be the total area from the x-axis to the curve, because area, again, can't be negative in that situation. I don't want you to get confused with that, though, because the answer to this question is -6.75, not 12.25. So
This just comes in handy when they're asking multiple questions.
yes.
Multiple answers.
That -6.75 from the y-axis over to 3, and then the other way around, like, in respect to the x-axis?
Yeah, so basically that. So when we were looking at this piece here, you're finding the area, so the 3 is going all the way across, and then the 2.45 is this piece here that you're subtracting off of that other value.
Okay.
So whenever you're looking at it, when you're plugging a number in, you're always finding from the x-axis to that number. And since I only wanted 2.45 versus 3, I had to subtract off that other piece from it. And you can do it for any number. Like I could have, instead of plugging 2.45, I could have plugged in 2. Like you can plug in any number you want. I use 2.45 because I wanted to split it at that point where it intersected so we can look at that concept.
So it makes more sense. Basically, off the right rather than off the bottom.
Correct. Yeah.
Full distance of area.
Yeah, this is, it's, yeah. All right.
So that would be like negative 675 would be more like the perimeter
No, it's not the perimeter. It actually is the space.
space.
Yes. So that negative 6.75 is the space in the orange and blue. It is the sum of the spaces. And remember, you have the below the curve is negative and above the curve is positive. So it is space. It's not the line. And that's the difference between derivatives and integration. In derivatives, we were looking at that curve because we were looking at the slope. Integration, we're looking at the space underneath that curve. Yes.
Where is at the end of the
Because I had negative 6.75 minus a negative 9. Which comes out to be 3.25. Because you get 2 negatives make a positive. So you get negative 6.75 plus 9. Did I screw up the subtraction? It might be. I might have screwed up the subtraction. That is extremely possible. Yep.
Oh, yeah.
You're right. I screwed up the subtraction. There we go. Now my notes are right. Couldn't have caught that earlier?
I was sitting there confused.
It's okay. This one?
So if you were to find the perimeter, how can you find the perimeter of that little shape there?
That's the distance formula.
So is distance with the equation?
So it's the, yes, in essence, there is ways to do it later. One of the things, so remember I said we can find volume of when you rotate shapes? That's actually pretty easy. As crazy as it sounds. Volume's actually easier. When we start to look at doing surface area, when you're looking at surface area, that's actually rotating the arc length, which is what you're asking for. That's arc length around a shape and figuring out perimeter. So that arc length ends up helping, gives you the perimeter of the shape, and then you multiply by how the rotation around. So the arc length formula actually is a lot more complicated to find than that, just doing the distance formula. But when you take Calc 2, we actually do that. So yes, you can find the actual lengths of curves. And you can find some lengths of actually crazy curves, because we'll do just this, which is simple, and we'll also do finding arc lengths for parametric equations and polar equations, which have a tendency to go back on themselves and all around and rotate and everything else. So we do all that. So polar and parametric is actually fun.
The first time I learned them was on my own in an online course.
Oh.
No.
On the online course, don't take any math heavy course online. Learn as a hard than physics.
All right, so let's look at this one. So this is y equals e to the x. And we're looking at, this is the area that I'm looking for, the space that I'm looking for. So what is the integral, or antiderivative, however you want to, we typically call antiderivatives integration. So what is the integral of e to the x? It's just e to the x. Now, as I told him, whenever we're doing a definite integral, you do not have to worry about the plus c. I know you get into that habit, it's fine. But yes, when we're doing definite integrals, you do not have to worry about the plus c. All right. So we're going to evaluate this at 1 and 3. So this becomes e to the third power minus e. And that's actually as far as I can go. So this, just so you can get a visualization of it, this is the area, all this area here. So that's all that area. And that is that area right there. So that's why we're subtracting that off, because that's the piece I don't want. And that gives me the final curve part that I want. So that's why you're always taking away, you're working from the y-axis over, and you subtract off that direction. So if we were on the other side of the x-axis, again, you're working from the x-axis over. So the biggest negative number that you're going to have is going to be the first number you're going to have, and you subtract off the other one. Because we're going always from the x-axis over.
The biggest being the smallest.
Well, in essence, it's the biggest negative, which is not necessarily the smallest. Because negative 1/4, the 1/4, it's, just trust me. Negative 1 million is not a very small number. It's a very low number, but it's not a very small number.
Yeah, again,
This is where that language piece comes in. It's a matter of how, and that's really why I spent a bunch of time talking about area, because we have a visualization of what area means. When you're on the positive side, yeah, the closer and closer you get to 0, the smaller it's going to be. So the farther you get to the left, the smaller it is. But once you cross the x-axis or the y-axis and go to the other side, once you pass 0, when you get further and further away from that, that number is getting larger or negative. It's just, it's lower, not necessarily smaller or larger.
the other one makes more sense.
Yeah, so that's how you gotta think about it.
So we have a negative 27, right? Negative 27, this is back in the after 1.
Okay, I'm like, where do we see negative 27?
Wait, negative 27, that's one example 1.
Yes. Negative 27 over 4.
And then you got the negative 27 before. What does that mean in the context of this problem?
In terms of the problem that's on the screen or the problem I was just doing?
Wait, no, never mind. It's below the x-axis. That's why.
That's why it's negative, yes. And in this one, e to the third is definitely bigger than e. So if we were going to do this out, just to get a specific number, e to the third minus e is approximately 17.4. So this is approximately 17.4. And it's positive. And it's above the x-axis, so that makes sense. And there's nothing below the x-axis to lower it down, so this one's all there, so that would be a positive value in that case. Yes, some will. If you hit shift and equals, or shift and enter, or second and enter in that case, it'll give you the exact answer, or the approximate answer. There is one to do it. What's that, the 89? Oh, it is the diamond. It is the diamond, yeah.
When,
Add some.
so when we're dealing with big numbers, and it doesn't tell us to what round, what number to round is close to, which one is probably the most, I guess, safest to do it to?
If they don't tell you to, so this is one that's going to be a preference of the teacher, believe it or not. If they do not tell you to round, in mathematical sense, you leave it as an exact value. So your answer in this case would be e to the third minus e. If you are going to use this in something else, and you need that actual number, then it depends on the context of what you're doing. If we're talking about money, 2 decimal places would make sense.
Oh yeah, but I mean,
So in this case, I'd want to see e to the third minus e. If the teacher doesn't tell you what to round to, give them the exact answer. Don't even put down to 17.4. The only reason I put down 17.4 is because I wanted you to see that it was positive.
okay.
So yeah, if they don't tell you to round, assume the exact answer. In this case, it's e to the third minus e. Because that gives you the most flexibility to do whatever you want with it after that point. So in this problem here, you'll notice that my original answer was negative 27 over 4. I would have expected to be left there. This one happens to come out to be an exact decimal of negative 6.75, so putting that wouldn't be wrong. But if it was 28 over 3, you couldn't write an exact answer. I'd expected to see it as 28 over 3. Just leave that number there. Don't go any further than that. Okay? Does that make sense?
Yes.
So, and any good teacher will, if they're going to tell you to round, will tell you what to round to. It should not be something you're just going to randomly come up with.
Okay.
Because context matters in those situations. All right, let's do an easy one. All right, you find me the area for this one. So what does what's the antiderivative of this?
Who you go to?
There we go. That might be the answer, but what's the derivative? What's the integral first?
Oh, 1/2 x squared minus x.
Good. Don't forget the minus x. Very important. All right, so the nice thing is a lot of times the 0, you don't really have to do much with it because a lot of times the things are just going to all cancel out anyway. So the 0 kind of is nice. So that's going to be 0, so I don't have to worry about that part. So I just actually have to plug in the 3. So I got 1/2 3 squared minus 3. So I got 9/2 minus 6/2 equals 3 halves. And actually, we could figure this one out because it's a triangle. It works out kind of nice. The area of that one is 1 times 1 divided by 2, which is 1 half. And the area of this one is 2 times 2 divided by 2, which is 2. So you do the 2 minus the half is also 3 halves. So, good. All right, let's move it along. Okay, so few integral rules that allow us to do some stuff. While these are technically definite or definite integrals, these rules work for any integration. If it's a constant, you can just pull out the constant. So it's in essence just a constant. And if it's a definite interval, it's going to be times whatever those are, because if it's a constant, it's just the constant times x. So you're going to plug those numbers in. If it's addition, you can take the 2, split it up, and do the addition of either the integral of each piece individually. That would be fine. That also works. And since it's addition, it's even if you can flip them back and forth, it doesn't make a difference. So, and the same terms would go on both. So you can see here a little graph of the additional one. So like there's my f, there's my g. You put them both together, it's basically adding those 2 terms on top of each other. If there's a constant times a function, you can just pull that constant out. That comes into play a lot of times when we're looking at, especially circles in like 2 pi r. You can pull out the 2 pi out of the function completely and not even have to worry about that part, which is going to come in handy quite often. So same concept that A and B stays. Things just like addition, you can do subtraction. You can split them up there as well. Notice you can't split up addition, multiplication. You cannot split up division. Those don't work as nicely.
Oh, it's just a constant. Okay.
Yep. Yeah, this one's just a constant.
Yeah, they look similar.
So, yeah, this one's a constant. This one is a constant times a function. So you got to remember, if it's just a constant, when I did the integral of that, say it was 3. The integral of that's 3x. Okay? So that's where it's making sure that you have that x term there. And then the x would just be whatever b minus a is in that situation. If you have a constant in front of a function, it's actually a lot easier to pull that constant out entirely and just not worry about it until at the end. All right, find me my answer for this one. All right, so we've got 4x plus x to the third. Is that correct? Is that what everybody got? All right, so again, the zero nice thing cancels that out, so I don't necessarily worry about that one. So 4 times 1 plus 1 to the third is 5. Very good.
Is there an example where we have to do an integral rule?
What do you mean integral? You could have done it on this one. Because the integral from 0 to 1 of 4 dx plus the integral of 0 to 1 of 3x squared dx, that's just 4x. I could have brought the 3 out in front of this.
Good that at that point you're just overcomplicating.
Correct. This is why we didn't do that. The concept of the rules now is it's just telling you what you can and can't do, really. So in essence, why I showed you this wasn't so much that you were actually going to do a lot of this. It's more the fact of you can't do division and multiplication. So I didn't want you to go, oh, I can just split up any way I want. It's like there's certain things you can break up and do individually and certain things you can't. So for a good example of this, here's one. Actually, that was the last problem I had written up anyway, so I can make some up. So here's one. If I did this one from 0 to 3 of the square root of x minus 1. I'll let you struggle for a minute or two. See what you guys come up with. He's like, yeah, no, I'm just not going to struggle.
Yeah, I'm doing some wacky stuff. What am I doing here?
What did you guys try?
Okay.
First of all, before I even go on, you cannot do this problem with what you know right now.
Okay.
Yep, okay.
What did you try?
Okay,
So I can dispel all the little things that you're trying to do.
So I just 8 into 1 half, right? And then I did plus 1, which is 2, which is 3 over 2. That's divided. We divided that by x minus 1. It's a complex fraction, so I did 2 change flip. And I got 2x minus 2.
Okay, believe it or not, you're not as far off as you think you are.
Oh, really?
So you actually, algebraically, you did everything fine. The problem, though, is think back to if this was a derivative, could you do what you did?
No.
Why?
Because it's like
What would we have to do if this was a derivative?
it was a negative way.
We'd have to do the chain rule.
Oh, yeah.
Okay?
Wait, chain rule. Okay, yeah.
Yeah, because you have a function inside of a function.
Wait, so it's how negative 3. Okay.
Right. Well, yeah, but it doesn't make a difference. We have a chain rule here because we have a function inside of a function. So in integration, what it's called use substitution. It's called the substitution rule, and we're going to do that next week.
Oh. What's the point of doing that?
I literally just wanted to show you a problem that you couldn't use the rules for. You're actually, what was the purpose of the rules? This is because there's certain things that you just can't do. What I was actually worried that somebody was, and now I'm going to put it on the board because somebody's going, yeah, I did that. I didn't want, this does not equal this. I was worried somebody was going to do that. Split up the square root. That does not equal that.
I had thought of
Yeah.
trying to deal with that.
Which is, that's the first thing that I figured was going to come into people's minds.
Yeah, the issue with that is that
Right. You also can't split up, you can't split up a subtraction in
it's
like,
2 to 1/2 power.
right.
That's the function inside. If
Yes.
it was just a function inside.
Yeah. So you can't just break up square roots like that. You can if it was multiplication. You can't if it was division or subtraction or addition. So that doesn't work.
So if it's like to the square root of 2x, you can do that, right?
If it was,
Square root of 2x, and you could just divide it by, and you could just make it into square root of 2.
so this one actually, yes. So, okay. Actually, this is a good use of the rules. So we'll do this one actually. That's a very good problem. I like that problem. So this one we actually can use the rules for, which is actually very nice. We're going to split this problem up. Because it's multiplication, I wouldn't have come up with this problem, so that's actually a good call. I can rewrite this problem as this. Because it's multiplication, I can break up the square root. Now, that's a constant. So this problem, I could pull that out. And now I'm just dealing with x to the 1/2 power. Which now I can do the integral of that one. So I got the square root of 2 outside. What's the integral of x to the 1/2? Again, we add 1 and put the fraction in front, or divide by the fraction, right? So it's x to the 3/2 divided by 3/2. So equals the square root of 2 times 2 x to the 2/3 or 3/3 halves divided by 3. And then we're evaluating that from 0 to 3. So that you can do. Yes, it's messier. But that is actually a good use of the rules where we can pull out that square root of 2 and we don't have to worry about that when we're doing the actual integration piece. First one I'm going to show you next week when we actually do your substitution. I never said I was playing fair. All right, find me this one. You can do. Find me this one.
I get an error.
I don't know.
Is it? Oh. Oh, okay.
All right, so what's the integral first? So you should have gotten 1/3 x to the third minus x squared plus 3x, and valuing from -3 to 2.
Oh, wait, that's. Oh. So, 30.
So, one second, I don't know, I don't have the answer.
We get 31.6666. So,
All right.
So it would be 31.
I think that 167 over 10.
I don't know.
Wait, what?
We're about to do it. You should have gotten 1/3 x to the third minus x squared plus 3x.
Oh,
Yes.
Okay.
okay, I did the.
So if I'm plugging in 2, because I do that first, 2 to the third is 8, so 8/3 minus
God.
4 plus 6 minus -3 to the third power is -27 divided by 3 is -9. -3 squared is 9, so it's minus 9, and then minus 9.
27.
Nines are wild. All right, so we've got in this case negative. Actually, put it on top. So we got -27 there, and on this side we've got that's 2. So we've got 8/3 plus 6 to 14/3. Sounds about right. So I've got 14/3 minus a -27, so that's plus 81/3. So I got 95/3. And if we divided that, it should come out to be 30. Yeah, just almost 32. It's like 31 point something. So yeah, this is why I was saying, don't round, leave it like that. Leave it as 95/3. And your calculator can do that. Huh?
Yes.
Yeah, so just leave it as a fraction. You could literally put 14/3 plus 27, it'll give it to you as an actual improper fraction like that. So just leave it like that. So save yourselves a lot of trouble. So yeah, you got 95/3. Now notice this one is all above the x-axis, right? So it's obviously positive. And that's one of the other things you can start to look at. It's like, if you throw these into a graph, you can actually start looking at and seeing if the answer you get makes sense. So, you want to try another one?
I think I get it.
What would you do that same domain to the -3 of the square root of 2x? Like you're just have a square root of -1.
Right, which wouldn't happen. You couldn't do that. Because you have to, so remember what I said at the beginning. It has to be continuous over the interval. That square root would not be continuous over that interval.
So like would you say like it doesn't exist with -3?
No, but you couldn't use -3 for that problem. Because the -3 is not in the original domain. So that function is not continuous over that interval. So therefore you cannot find the interval of it. It would not, no. But that's what I'm saying. You could not get a problem like that because that problem wouldn't work.
I was thinking like -3 to 0, it basically doesn't exist, but from 0 to 2 it does.
Right. So your interval would have to be 0 to 2.
Okay, so it has to be 0.
Yeah, it has to be continuous. So it has to be within values that would work for it. So since the square root can't be negative, you wouldn't have those values. Now, if it was cube root, you could, because it does work over there. All right, next week on Tuesday, we're going to do the fundamental theorem of calculus, which is in essence which we just did. So it's not going to be that major. Actually, you know what? I'll briefly go over it, but I actually might just start use substitution. Oh wait, never mind. I still got to do indefinite intervals. So we'll do that on Tuesday, and then we'll do use substitution on Thursday, and then we're done. And I will give you your chapter 5 test on that Thursday. So, which you'll take home and do it and review for your final. Your final exam will not have intervals on it. Your final exam will just be derivatives. Okay?
Wait, all it is just intervals.
Your final exam? Yeah. It's going to be chapters 1 through 4. Well, mostly chapters 3 and 4.
Yeah.
So, because that was the derivative stuff. I'll probably have a couple little things on there from chapter 1 and 2, but it'll be the majority of your final exam will do chapter 3 and 4, because that was the meat of this class. Okay. The final exam's in person. Yeah. The chapter 5 test you're taking home, and it'll be due the day of the final exam, which is 2 weeks from 2 weeks from tonight. So 2 classes.
Oh, so
Wow.
reviewing in class on Tuesday.
Reviewing for the final exam.
That's
I think it's the 15th actually.
Oh no, yeah, Thursday. Wait, Tuesday or Thursday?
Thursday. It's 15th.
Okay, yeah.
Yeah.
Okay,
Because the semester ends the 18th technically. So yeah, we have class the 5th, or I mean the 6th, which will go over indefinite integrals and the fundamental theorem of calculus. The 8th will be the use substitution, and I'll give you the chapter 5 test. The 13th will be a review for the final exam. I'll do the whole night of a review for the final exam, and the 15th will be your final exam. Nobody is in this room prior to this. I will be here at 4 o'clock that day. So if you would like to come early, if you can, to work on the final exam, you're more than welcome to. So I'll be here at 4 o'clock on the 15th. So I'm hoping it doesn't take you that long. I'm hoping.